okay? Okay, awesome. That was annoying. I just refreshed and I guess it works. Okay, so yeah, this is a COE538 tutorial. I guess started off a bit late. Should be fine. We're going to be looking at some midterm questions that I gathered. To be honest, the exam is not too hard. Will this be recording? Oh yeah, so I should say it's not going to be recorded, but the notes are going to be posted. As for the chat, you guys feel free to unmute, just type in chat, whatever. It looks like the permissions on chat are good, so you guys can just type to everybody. You can message me directly as well if you want. I'll try and keep up with the chat. Like just sometimes I just forget and miss them. Okay, yeah, should be good to start. Okay. So I prepared us some questions we're going to go through. From year to year, the questions are pretty much the same thing. So as long as you're kind of confident with your HCS 812 assembly language and you've solved questions like this before, you should be fine in the midterm and final for that matter, to be honest. I'm not sure, when I took the class, we were given the instruction set alongside our midterm, which was really helpful. For some reason, when I did a tutorial in the summer, they said they weren't getting it, which is odd to me. I've attached it to the end, and now like it'll be on the document I give you guys as well. It's just a paper. You guys, let me know if it's on your shell or anything, if you have access to this document, pretty much. But it's just the entire instruction set. Yeah, it will be given. Yeah, okay, good. Make sure it's like to be honest, it's kind of your best friend on the exam. It's kind of a bit of a cheat sheet for free. If you kind of understand how to read it, it helps you. It'll help you a lot. Uh, so I really recommend kind of understanding what the actual lines mean. You'll see. I'll try and use it as we do questions. Should be up on the, yeah. You should have, either way, you're gonna have those one I have here, and it's probably gonna be the same one that they have on the final or the midterm. I'll try and, as we solve questions, use like this one I have here just to kind of show you the thought process and show you how to kind of look for what you need as you solve questions. But for the most part, yeah, it shouldn't be too difficult. And yeah, okay, we can just get started probably. Like I said, though, the questions are very similar year to year. So if you have past midterms that they provided on the course shell and you're confident solving their questions, it shouldn't be too bad. But let's start. So first question you might see after some multiple choice, which we can solve at the end if you guys have any questions. But first question you might see is just essentially filling in the assembly lines, the HCSA 12 instructions, and then we're going to do a little calculation at the end for how long this program will run for, pretty much. Where will notes be posted? I just kind of send them to the person that contacts me through the department, and then I think they post it for you. I'm pretty sure. Yeah, I think it should be posted on your shell, but we'll see. But yeah, so we'll get started here. First question. So let's just go through and solve it line by line first, and then we'll worry about the calculation at the end. So load register B with 0F. I'll assume you guys haven't really looked much at the instructions, although most of you probably have. Just to start it off quick, I'm just going to look at the back. Load register B with 0F. It's a pretty easy one, but I'm just going to go and find the instruction. I know this one is going to be LDAB. Oops. You can see it at the top, right? Load accumulator B. And so this is an easy example, but it's nice to be able to see not only the actual like what it's doing over here, but also the kind of layout of the instruction as it's there, as it's kind of presented to you in the assembly. So again, this is an easy one, but I just want to kind of get you guys familiarized with looking at those instructions because you'll see how much it helps later on. So yeah, we'll just go ahead, fill this one out, LDAB. Next one is load register X with 8. We won't look again because we know roughly what it's going to be. This one is going to be LDX. No operation. This is a simple one as well, just NOP. Nope. So let's see this one now. So decrement register X and branch if not equal. And you're looking, if you see, we only have one kind of slot to fill in. So we want to find a pretty, there should be only one instruction that fits here. This is a bit more of a complicated one, so I'll look for this one. And remember, we're trying to decrement our register X, and the next one's gonna be decrement register B, and branch if not equal, right? One that looks like it would fit for this is DBNE, right? So continue the next instruction, decrement counter and branch if not equal to 0 pretty much, which by default it's checking if it's 0. So we could probably use DBNE for both of those. Decrement register X and branch not equal, and we'll say D. And the next one is the same thing, but with the B register instead, right? So cool, the easy part is kind of done. We solved this assembly here. Now we want to kind of get the runtime in nanoseconds, e-clocks. So they provide the e-clock values for each kind of line, and then at the end, we'll just multiply it by the actual time per clock just to get the final number. But essentially, for the most part, when you get these types of questions of like e-clock and time, most of the time there's going to be a loop at some point in it, and if you kind of are used to reading this assembly already, you might have already seen it. What we're doing here is initializing. So our initialize register B with 0F, load register X with 8, whatever, no operation. But notice how we have a little, our label there, and I guess here as well. And we're going to be branching if not equal to these things. So essentially, this is kind of a little counter or a little loop if you've noticed it already. So when we're trying to solve the time, we're going to go first ones. We're just going to kind of do one by one. It's not too bad. So load register B with 0F, that's not in the loop. So we can just add like a 1 here. I'll just add the 1 up here. Next, we're going to be in this loop, but and essentially the hard part of this question is determining how many times this loop runs, right? So you kind of have to work with the question and see what they give you. First of all, we're going to register, we're looking at register X here because the first kind of branch instruction we're trying to decode is this DBNE here. That's the first one we're going to hit. So decrement register X and branch is not equal. And we're going to be branching to this in LP, in loop. So let's see what's happening here. We go through here and we go through here. And we do that each time until register X is equal to 0, essentially. So what we can do here at the bottom, just to kind of simplify it for us, is we see this is 1 e-clock here, this is 3 e-clocks here. So let's do a little 1 plus 3. And let's think about how many times this is going to run, right? If we're starting at 8 and we're decrementing it each time it's running, this is going to run 8 times, right? Before it's 0. And then on the last time, when it's 0, it's going to break out of this loop, essentially. One thing to look out for is, I mean, this kind of caught me as well, and a lot of people I know that when we wrote this, is that the off by 1 errors are really annoying. Usually they're not too strict about marking with those, but you know, you might kind of in your head like fumble a calculation, like since it might be starting off a 0 index instead of 1 or vice versa. So you can try, if it's like small numbers like these, to literally run the loop in your head. Up to you though. So I know this is going to be times 8. Oops. So we broke out of that inner loop. Now we're kind of going on to the outer loop. Decrement register B and branch if not equal. But because this is kind of all intertwined in one, we're going to be running this inner loop each time we actually run our outer loop as well. And so it's kind of the same concept as the last time, but one thing it's not going to be as simple as just like handling just these two. Let me close these. It's not just going to be these 2 lines anymore because we're actually going to be running through these lines as well, right? So what we're actually going to do now is wrap this one more time and multiply it by how many times this outer loop is going to run, right? So decrementing register B and branch around equal. We have to see essentially how many times is this loop here going to run. And this is listed as 15 here. 15 times this loop is going to run. Did I mess that up actually? No, it looks good. So 15 times. And then, yeah, that should cover the loop area section. Again, the loop area is the trickiest part usually. And I actually picked a tough question here because it's like two loops kind of in together. How do you know it's running 15 times? Let me double check. Ah, you know what? I messed it up. You're right. I got a message. 1 second. I missed a number. So this is how tricky it is because when I did the first inner loop, I didn't take into account the outer loop. Let's see what's actually going on here. So where can I find this practice midterm? This one, I don't know. Wait, let me just go through these. Okay, I'll get this either f equal to 15. Where can I find this practice midterm? Like these questions exactly, I don't know if you guys have access to these necessarily. But to be honest, if you have any on your course shell, you should use those. Yeah, these questions are pretty, I think this is from 2012. I don't know, but I don't know if you have access to these, so I don't want to just send them to you guys. Anyway, let me redo this question because I see where I went wrong. So, well, the mistake I made, we'll start with brackets again here, is that we have to run this outer loop. This kind of outer loop is running, the inner loop is running each time the outer loop runs, if that makes sense. So it's kind of like a nested loop here. So what we should do here is start first with the 2 e clocks from the outer loop, from this line right here. So we're going to say 2 here, plus, and then now we'll go into that inner loop for each kind of iteration of that outer loop, right? So that our inner loop now is 1 e clock here, plus the 3 e clocks of the inner loop. And how many times is that inner loop running per iteration of that outer loop? It's going to be run 8 times, just like we said before, right? Because that counter in x is 8. So we want to go down 8 times before we hit 0. So, and now one more thing. And now we're going to be running our last part of the outer loop, which is 3, and close it in brackets. And now we're saying how many times does question starts to start from init. Yeah, the question says to start from init. So that's the one we added at the top, right? I'm kind of going vertically. And so yeah, so this is our entire kind of inner loop right here visualized. And now we want to say how many times is this outer loop running, and it's going to be running 15 times for the 0f, right? I can just be consistent and say 15. Why 15? Because 0f, I mean, in hex is, well, if you think about it, sorry, just the first one is f, so 15. Why is it 2 in the inner loop? Doesn't it only load once? Why is the 2 in the inner loop? Well, the 2, yeah, the 2 is in the outer loop, not the inner loop. The inner loop, let me close it with the green. So inner loop can be simplified essentially by this. And then the outer loop is the everything around that. That one, you can just kind of forget it. It's just the init. Once 15 is, do we have to go through the process of decrementing 8 again? Yeah, so good question. It's this. I kind of picked a tough question for this one. I don't think you guys are going to get the question this tough. But yeah, it's a nested loop, right? So if you look at it, if you kind of run through this logically, we're initializing our outer loop to 8, right? And then we kind of hit these 2 lines here, which is our inner loop. Why is 2 being multiplied by 15? So let's go through it. So we have these 2 lines, which are our inner loop, right? And these are going to run 8 times, like, right? It makes sense. This one's pretty straightforward. But look what, after these 8 are done, we're actually going to go to the next line, which is here, right? And what's this going to say? This is checking B now. And B is 15 times. So this guy is going to decrement B once, right? So 15 times we're going to go. And we're going to go back to out LP. And if you notice, when we're back at out LP, we have to go through this inner loop one more time again. And that's what the nested for loop is here, right? And that's why we're going through the inner for loop each time we go through the outer one. Why is the 2 being multiplied by 15? Because the 2 e-clocks of the kind of out this line here is included in our outer loop, right? That's the first line of our outer loop. Once 15 is, yeah, so yeah, and once 15 is decremented to 14, do we have to go through the process of decrementing 8 again? Yeah, each time, right? Yeah, if you can kind of logically follow it in your head, each iteration, you can kind of literally jump to each line mentally and you can kind of see that that's the case. And so, yeah, so we have this. And then lastly, once we've broken out of both loops, we have our last one e-clock down here. So we can kind of add this all together. And this adds up to, you can do the math yourself. Oh, sorry. Something about this. Let me open that up. Cool. So, okay, so this ends up adding to 557 e-clocks. Is the one top of plus? Yeah, yeah. Like the top and last are like kind of in it and the last lines, the loops at all side. So we're just kind of adding them as constant here. So equal doesn't just yeah. Well, so doesn't out it. So the out loop is running times, and we can kind of under that, right? Like forget what's getting these two lines in the middle. Just look at out. Like look at our X register is F. Oh, am I just cutting? There now, I hope so. Let me unplug and replug. Hello, hello. Sounds good. Okay, perfect. Technical difficulties are hitting this one. Okay, so yeah, 55, 57 clocks, that's the hard part done. And we're told that one e-clock is 40 nanoseconds, right? So we're just multiplying this times 40 ns. And we're given 2.229 ns. And that's the final answer for this question. So yeah, I kind of scuffed at picking a hard question like this with a double loop. I double loop, that's tough. But what I was answering to the other guy or girl before I refreshed was, yeah, so each time we run that outer loop, if you notice, like this little out loop here, it's jumping up to this second line, but it'll go through those two lines underneath it again. It's not necessarily like, those aren't two different loops. 2280 and right? Is it 2280? I don't know. I just kind of have the number written down. It's me. Let me run it quick myself. Yeah, 2280. Okay, cool. And so, yeah, that's pretty much that question. If anybody has a question, you can say it now. But yeah, the trick is to kind of, yeah, it's difficult to kind of imagine it is on a double loop, but yeah. Okay, looks like no more questions. Yeah, you can always feel free, guys, if you want to unmute, ask a question, or even say go back to another question. We can do that as well. But yeah, we'll go to the next one. So next question, again, very common. You like, I will say that like you will see this question on your exam, like something of this style. And I put two of them even here because I'm pretty sure you're gonna get one of these. Uh, so essentially what we're doing is we're given a bunch of assembly code and we want to output stack address and stack content. So we kind of want to run the code ourselves like mentally and be able to output what the code would output if it actually ran on the microcontroller. So I got kind of an easier one here first. This is the first time I'd say it's really going to be helpful to understand what the instruction set sheet, and I'll show you why in a second. So let me just open up what I have here. So I'll kind of run it like I won't cheat and jump to this jump subroutine. Maybe some of you guys have already seen that, but we're starting at org memory address 4000, so that's where our program is beginning. LDS is we're loading the stack pointer with the address of, or sorry, the value of 3000. And so that's where our 3000 comes from on the beginning stack address. And so from here, we're kind of just running the program on ourselves, right? So LDAA, if you kind of, I think you guys might be given a little diagram of the register layout of the HCS A12, which will help a lot. Because right now I don't have one on me, so it's kind of going to be more mental. But LDAA, we're just loading A with 32 hen hex. And this is an interesting line here, jump subroutine MEL. So we see our MEL label here, that's where we're going to jump to. But what exactly is jump subroutine doing, right? Because again, we want to understand what's going to happen to the stack as this program runs. So let's go and jump down exactly to the jump subroutine instruction and see exactly what it's going to do. It's on the left here. So look, let's see what's happening here. And you can see right away, it's a dead giveaway that it says stack pointer. So that's how we know it's modifying the stack. And if you know what the jump subroutine is doing, it's going to jump to another subroutine is what it's saying. But the important part is that it's also going to modify our stack with a little return address. So once that subroutine is over, it'll come back to where it left off essentially. And the important thing to look at is RTNH and RTNL. So return high and return low, meaning the two bytes of our return address, because it's 2 bytes, right? And those are going to be stored in stack pointer and then stack pointer plus 1. Let's go see what that actually means in terms of our diagram. So we want the return address. Essentially, we want to get where the jump subroutine is. And so when I said we don't want to cheat before, what I meant was we're starting at this 4000. That's where our program is actually starting, right? And so we kind of want to go line by line and see where this jump subroutine actually ends up being in the program memory, so to speak. So if we say 4000 is our starting point, right? And instruction length is given to us here, it's 3 bytes. And even if they didn't give us, you could kind of understand this. Like the actual instruction is going to be 1 byte and then 2 bytes for the address here. And then, yeah, pretty much. And then the next one is 2 bytes because 1 for the instruction, 1 for the upper end, and so on. And so we actually want to go through our program and get the address of that JSR because that's where we need that return address to push to the stack. So if we start at 4000, we go by 3. We're going to be at 4003. I'll just write each one. So plus 3. Next one, we're going to be at 4005. And then 4007. And this is where our jump subroutine is actually happening. Oops. So what do we want with this address, right? So remember it said, I'm not going to go back, but then return high and return low are pushed to our stack pointer, right? So we want to take our address that jump subroutine is jumping from and push it to our stack when it returns. But if you remember the order, or if you have the instruction sheet, I actually recommend that having the instruction sheet open as we go through this tutorial. If you saw the layout of how it pushes it to the stack, we're going to go low gets pushed before high. So in our stack content here, we're actually going to go, oops, make this black actually. We're going to put the lower half first, which is the 07. And then we're going to put the 40. And stack address is much simpler. Once you kind of get that starting point, it's given for us here at 3000 because we're like literally loading it with 3000. You can literally just go and fill it with each one kind of going up from here or down, however you want to look at it, and so on. And the next one's going to be longer, so it's the same thing on pretty much either one, on every single one. I mean, each one is a byte, so we're kind of moving the stack by a byte, of course. Sometimes I've seen it before, but I don't think they really give those questions anymore. They'll kind of like jump across the stack, so like that's why it might not always be linear. Just keep that in mind. So if it's like no kind of like jumps in the thought process, or if there's no jumps in the code that they kind of ask you to go, it's just going to be kind of decrementing up from that first stack address. So we pushed our jump subroutine to the stack already. So now we're actually at the mel subroutine, right? And all this is doing is saying push A. So whatever we have on A, we want to push. And we'll look at the actual instruction for this, just to get the actual layout on the stack. Push A is down here, right? And so look what's happening. Again, push accumulator A onto stack, essentially just saying A goes onto stack. That's it. And A is 1 byte in HCSA 12, right? So it's just no high or low, just whatever it is goes straight to the stack. And in this case, we loaded A with 32, so this will just be 32 as well. And that's this one pretty much done. Again, this one's pretty straightforward. The hardest part, I think, is but if there's no need to memorize the jump, right? You can just look at the instruction set and know that exactly how jump is going to react, so to speak, or like exactly what it's going to do. Which is why I say it's a huge help to kind of understand where to look in the instruction set. Yeah, you can cut out a lot of the guesswork and memorization if you just kind of understand that. Yeah, this one's not too bad. Can you explain this for instead 32 again? Okay, yeah. So once we finish our whole like jump subroutine, right? We're actually jumping to this mel label, which is just the next line anyway. But let's just assume we're making a logical jump here to the mel subroutine. Mel subroutine has only one line. It's just to push A. You got 40 and 70. Yeah, I'll explain it after this. So once we jump, so let's say skip out the first like 3 lines here. We only care about this last one, right? Because now we're in the subroutine. All we're doing is push A. Push A. When we read the instruction, all that's saying is push A to stack. Like nothing else funny, no jumping or anything. And we loaded A with 32 up here, right? So once like change the value of A, the value of A never changed. So once we just push A, just whatever's in A gets dumped to the stack pretty much. That's how we put the 32. And you're kind of going up on the stack here, right? The 2FF and the 2FE. So stack address, I mean, we're starting at 3000, right? Just because we started, in this case, we literally loaded the stack with 3000 in hex. And so we're just going up one by one from there. And I said earlier that if there's no like jumps jumps is a bad word to use. If there's no kind of like breaks in the code, sometimes they kind of try and trick you and make you like jump addresses or break addresses. But in this case, it's kind of pretty a linear like path, so we can just go one by one by one. And since stack is sort of infinite loop before it get pushed back, so the 32 goes to the top eventually. Okay, so I'll say the 40 and 7. Yeah, so since this is a sort of infinite loop, oh, did I change it? Can you guys not type? Yeah, you can type everyone. Okay. Yeah, the last line doesn't really matter, but it's just a branch forever. They just ended in like a, like kind of whatever loop, like or infinite loop they can just to kind of end the question. But do we have to write the number in hex? I would write the number in hex. I think if you want to be smart about it, you can, as long as you use the correct, like, correct, I don't know, format, you can write it in binary, you can write it in decimal if you want. How do we know that low is returned first? So I'll go and actually show you guys again what I did. So once we hit the JSR instruction, so let's remember again that our stack is kind of going upwards, right? It's like decreasing as we go up. But I'll jump back to the, oops. So if we find the JSR instruction again, it's down here, where I highlighted it, right? And look what it says is returning, right, on the JSR. So stack pointer minus 2, it just means we're decreasing stack pointer for 2 because we're dumping 2 values to it, right? But notice the, can you do example stack just one and linear? So notice how RTNH, RTNL, and it says it's pushing it to the stack and stack plus 1. And in this case, since we're decreasing upwards, stack plus 1 is actually the lower value, right? So essentially, we're getting the low value first and then the high value. RTNL and RTNH, which is the high. And when we go back, so essentially when we run that jump, before we actually, perform the jump, how come 7 become 430? So, well, because that jump is ran before the push, right? So once we do the jump, once we execute, like, let's think about it logically, right? We set our program to start at 4,000, whatever, that doesn't affect our stack. We set our stack pointer to start at 3,000 hex. Fair enough, we started at 3,000 over here. LDAA hex 32. That doesn't affect the stack, right? We're just loading the value of A with the immediate value of 32. So now we hit that JSR, and like we saw in the instruction set, JSR actually does affect the stack. It'll push it to the stack first, and then perform the jump. So that's why we want to push to that stack first, and then we'll kind of jump to the next block of code and see what that does. And so that's why once, like after we push our return value to the stack, because it needs to figure out how to come back, right? Then we can kind of look at what's that mel loop or, address, and all that's there is push A, which is that 32. It pushes in the address of stack pointer, then it pushes the content of accumulate A. Like, try not to think of it like going from the, like vertically going from the top to the bottom. Like we're starting at stack adjust 3000 and then kind of going down from there, because that's how the stack works. Because ideally, it's this kind of like a later topic that you guys are learning next semester. Stack frames, if we're starting at 3000, we kind of want to end up back at 3000 again after we're done, right? And so that's why you kind of will go down, 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 but eventually come all the way up. And so the way to think about it is, yeah, starting at 3000 and then kind of drifting away from 3000, but eventually you come back. As for the example of when it won't linearly, when it doesn't like linearly jump, I haven't even seen a question of it. I think for some reason that's stuck in my memory, because when I was studying for this, I found like a random question from like 2002 or something. I wouldn't worry about it. I like in all the material that I've seen preparing even for this, I haven't seen like anything like a break like that. But let's see. Will the stack address for the first row be 2 FFD? Please push A subtracts 1. Yeah, it would be 2 FFD. Exactly. So we're just kind of going on. I just left it at dot, dot, dot because you'll see in the next one we have a bunch more and it's the same concept. But you can see that as well. I mean, like, just to be crystal clear, to see exactly how much our stack address is being like kind of jumped down. If we go back to the instruction, let's go to like our push A one, right? Because that one was a kind of easy one to look at. Push A was down here. So let's look up what push A is doing exactly. I mean, this is doing it in one line compared to our other one, but it's saying SP minus one. So change the stack pointer, like subtract one from it, right? And then once we like subtracted one, that one value is going to be filled by the value of A. So we're just pushing A into that on our stack pretty much. And that's, I mean, that's what it's called, push A, right? Like, again, same thing on the JSR. Let me see if I can find it. The first thing it says is stack pointer minus two. So that means like we're gonna like it's pretty much saying that this instruction will change the stack pointer by two, and then it's saying the next line is saying what will be filled in those two slots, pretty much. Yeah, and it tells you kind of how to fill that in. So it's a bit of like a weird way to think, but again, if you kind of get used to seeing their things, and they really on the first page of this, which again you guys will get, at least so you guys told me, this page will kind of explain the I don't know, like what each kind of thing means, each operation means. But once you kind of practice a bit, you can kind of understand, and it helps a lot. So yeah, yeah. The 07 is the back end of the address, and the 40 is the front end of the address. Yeah. So like remember how we start at 4,000 because that's just like program start. We run a few instructions, and wherever our JSR is, it needs to return there after it's done the jump. Like that's just part of the instruction. That's what the instruction does, right? And JSR is being run at 4007, the address 4007 in hex. So what the instruction said on the instruction set like data sheet, and that's like a real data sheet, right? That's why I say it's pretty cool to learn. That's the actual data sheet for the microcontroller. They didn't make that, and it says that it'll first push those like the address that it was run from to the stack, and then make the jump. And so that's where our 07 and 40 come. I think if I do the next one, you guys will kind of understand it as well. Don't want to get hung up on just one question of this, right? So we can do this one as well, and let's kind of go through it together again. So same concept, starting at org 3000, right? Loading our stack pointer with 4000 this time, so we can fill it in first right away. We're starting at 4000. And this time I won't do like any dot dots, and I'll just fill it out like as we go. So clear A. We can go look at it just because it's a new instruction, I guess. Let's see what clear A is doing exactly. I mean, I'm sure it's clearing A, but let's see what the data sheet says, right? So we can see if it's modifying the stack in any way or anything like that. Clear A. Yeah, so clear A, it's doing an operation. It's just well clearing accumulator A, but it looks like it's not doing anything to our stack. So the only thing we should really look at it for is our like address in the program, pretty much. So let's see what we're doing. So org 3000, 4000, clear A, instruction length in bytes 1, LDAB, LDX, branch subroutine. Everything until branch subroutine isn't actually going to change anything on our stack, right? Because none of these are, like we saw org and LDS last time didn't, LDAA and LDAB don't, and LDAX doesn't either. So all of these are just kind of setting up here. They're not actually going to modify our stack in any way, and we're not going to change our stack address at all. But what I will do is I'll write down, because now it's going to be a bit more complicated, what exactly is going on in our registers. So if you guys, I'm not going to draw the whole diagram, but essentially, if you remember correctly, the B, so when we're LDABing, we're loading up B with $57, right? B is just a 1 byte, so I'll just say, let me make 2 boxes here. So I'll say this is A, this is B, this is X, right? Why do the bytes matter for the instruction length? You'll see again, right? Because last time, remember when we got the jump subroutine, we needed like the location of that jump, right? And we have a branch subroutine this time, so it's a pretty similar thing. But we'll look at it. We'll get there when we get there. Um, so we're loading up B first with $57. Easy enough. 57. I just wrote A there. We don't actually modify it, just so like just this is like roughly what the actual layout of the registers are. Not all of them, but this is what they are. And then we're loading X with 74. And just to be clear, X is it's double the size of B. It's kind of it's 16 bits, 2 bytes. But right, 74 is just 1 byte. So just to be very clear, I'll fill this out as 0074, and that's 2 bytes, right? We always take like leading zeros if it's not provided. And so these are our current registers before our branch. These are like kind of, I guess, our system as we are about to do the branch. So let's look at that branch subroutine and see what it's doing, because it's not a JMP or JSR this time, right? It's probably very similar, but let's just look at it to be clear. So it ends up literally doing the exact same thing, but I guess it's good to look at, I guess. So yeah, look what it's doing. Again, stack pointer -2. So it's decrementing it by 2. And then it's saying that, again, we want to do RTNL, RTNH, and it's going to the stack pointer and stack pointer +1. And then it's also saying subroutine address to PC, but we'll do that after. So this is when we're going to need that instruction length again, because we got to calculate where we are when we run that branch subroutine, right? And we're actually pushing to the stack the first time, but let's calculate that after. So I'll write it down here again, sure. So 3000, yeah, we're starting at 3000, right? Or sorry, stack pointer 4000. I think I almost made a mistake. Let me just double check that instruction one more time. So this is RTNL, RTNH. Let me check jumps one more time. Okay, and we'll go back. So stack pointer there. So I was okay. So we're starting our program at 3000 again. Looks like the answer on their midterm might be wrong because yeah, if we're starting at 3000, they started at 4000, which is a mistake. Whatever. We're starting at 3000. That's where our program is, right? So we'll start at 3000, and then we're going. So our instruction length for the next one is 3. So we'll go 003 plus 3, and then 1. And again, we're just kind of going. We're just running like we're seeing the location of our memory once we arrive at that branch subroutine. And then whatever, we'll just go to. So I'll just end up adding. So we'll go 3 plus 1 plus 2 plus 3. Yeah. And this ends up being, should be B. And I think that my hex math is correct. I hope so. You guys can correct me if I'm wrong, but we should be at the location of 3000B. Or yeah, 3000B once we get to the branch subroutine. And so yeah, that's the value again that we're going to be pushing to the stack, right? It's the same concept as the jump subroutine. So first thing I'll do is fill up our stack address. I'll increment this by 2 here. And oh, it's E. Oops. Oh, okay. You can see that little scuffed hiding it, but yeah, there's the E, I guess. And then what values are going to go in there? So remember the address that we're calling the branch from is at 3000B, and we go, remember, low first, then high. So what are we going to do? The low in first, 0B, and then the high part, which is a 30. right? And that's up branch. We're kind of covered on our stack. So now we've branched to our little our subroutine, right? And our subroutine has two things: push D and push X, which you might remember from um, our last one. We had push A, right? It's a bit more complicated. The reason and this is why I drew this out from the beginning. So what we're doing first is push D. If you remember correctly, it's in the data sheet as well. How did you get 3 FFF? Well, we're just going one down from 4,000. It's just the next address. And like it's the same concept. Again, no breaks here. So you just literally go one by one in hex until you get, and you'll see that's what it ends up being. But so we're going to push our D register first. And so if you kind of are familiar with this stuff, their D register is actually our A register and our B register as one 16-bit or 2-byte register. And since we never loaded A, we're just going to assume that's 0, 0. So let's just fill that in as 0, 0 for now, just for ourselves. And so when we're pushing D, again, we always go low and then high when we push to the stack. So let's write in our addresses first. Push D again if we're pushing 2 bytes. And we're pushing low first. So we're pushing the low part is the B, right? We're going to push in that $57 first. And then we're pushing our A register, which we're going to assume was 0, 0. Because like let's hope I think set it before it was called. So that's 0, 0. And that's our push D, right? And I hope that makes sense because we're just using D register, which is just built out of the A and B registers. A was cleared. Yeah, oh yeah, clear A. You're right. I forgot about that. And so yeah, last one now, push X. Our X is easier because it's just the one big register, but it's the same concept, right? Again, we'll add 2 more here. And low first, so 74. And 0, 0. And that ends it up. That's pretty much it. And so that's the question here. Same thing as the first one, just a bit longer. If A wasn't cleared, there'd just be garbage in it. Well, if A wasn't cleared, we have no idea. It could be 0, 0. It could be like whatever the last, like, because we're starting our program at 3,000. So the HCS 12 would start us at 3,000. If the program before us or whatever was running before us left something in A, it could be any value, right? So, but in our case, we got the clear A, so we know that it's 0, 0. So it's like something, it's like a root of a past program. It could be, right? So, but yeah, the clear A clears it up. So I think with that second one, it should like kind of clear up this question. Where did the 0, 0 between 5, 7 and 7, 4 come? So yeah, so remember what I said, we're not pushing B directly this time. We're pushing D, the D register. And if you, I don't have the paper on me now. Let me see if I have a decent picture of it actually. It's a D register. Yeah, okay, I don't. But let's just we like this is a real thing, but just trust me, bro, right? But you can verify this in your like textbook or whatever documentation you got on the HCS 12. But the D register is just built out of the A and B. Like it's the same thing. You can take the D and take the 2 bytes or individually address it as A and B. And so, but when we're pushing D, right, we're just pushing the entire D register, which we set as 5, 7 and 0, 0 initially on the program. And that's so, and when we push D, we're just pushing low, high. So I can even, just to kind of make it a bit more clear, say this is our D, that's our X. Yeah, and the last one, I'm not going to write it because it's a branch, but yeah. And hopefully that clears up this question. I mean, again, be comfortable with the instruction set, like actual paper, and like you see how much easier it is. Like I didn't have to memorize any of these instructions. Just cover it, and even tells you like exactly what it does to the stack. You don't need to memorize like, oh, branches do this or that. You know, it's very clear about what's happening. It's a real data sheet, right? That's what I kind of liked about the class structure. But yeah, it's not too bad. Why do we push X first? we didn't push X first. Remember how we started from the bottom up? We started 3000 and we work our way up. So like, look what happens. Branch to subroutine. Yeah, BSR is branch to subroutine. But look what happens. Like, we're starting from the bottom, right? That's why I put the 4000 at the bottom. Because when it looks at our stack pointer, it kind of goes up, or that's just kind of how it's done. And we're doing LDAB, LDX. BSR is our first kind of stack modification, and that's our first one at the bottom. This is our whole. I guess I'll write the BSR here, but the actual first thing we're modifying the stack with is the BSR. And then what's the next thing we modify the stack with is this push D. And so that's what our D register is getting dumped to the stack. And lastly, push X. So we're not doing X first, we're actually going the other way. Layas too. It says, yeah, we don't care about layas in this case. Like, yeah, we don't care because it doesn't go any further. But I mean, we can look at what it does. But once you filled out all the boxes on your paper, it's done, right? And because like last time they just used the branch, which technically, if you think about it, actually I don't think branch would, but let's just assume that was something that modified the stack. It might modify the stack. We don't really care. Our thing is filled out, right? But let's just go look at Lias for the fun of it and just see what it does. Effective address equals load effective address into stack pointer. Yeah, okay. So this is, I guess it just loads like the address of where the LEAS is called into the stack pointer. It's not really relevant for this question. Yeah, that's what I would assume. But yeah, that pretty much wraps up that type of question there. The stack questions. I'm like certain you're going to get one of these questions, but you can see it's not too bad. Just kind of follow it logically. You kind of have to get used to using like working your way up from the stack, or I guess down. I don't know how you want to look at it. But as long as you know the layout of the instructions, like again, you have the data sheet, just look at it. You can see how it modifies the stack exactly. Yeah, shouldn't be too bad. Just try, like be careful with your little like push D, push X. Yeah, if you do like one or two of these, you can kind of get the gist of it, to be honest. So if there's no questions, I'll just go to the next one. Okay. The next question looks a bit scarier. It's really not. So essentially, we're going to be running a 7-segment display on our little ACS12, ACS12, and we have a program to do so. We only have to fill stuff in. So it might look a bit intimidating, but most of it's filled in for us, and it's kind of telling us what to do in the comments. So we just kind of have to follow along with the comments. And again, you're going to get this information with your actual, you're going to get this information with your midterm. And I also assume you have it in study material to kind of understand when the HCSA12, like when it does what, but it does a pretty good job of telling us exactly what to do. So let's start then. So this question, it's going to be very similar like every single year. The only difference, and I'll highlight exactly when it matters, is our input and output pins here, our PB and PP pins. The only thing that changes is our kind of what I use, because when we write to them or read from them, it might change based on the numbering. But again, I'll point it out. So let's see what we're starting with. Configure port B as output. So, and we're given the move B instruction here. And so you'll see there's kind of three. I see two. Okay, so in this, maybe we'll see one later on. But there's kind of three ways to kind of write to a register, right? When we're talking about these. Oh, someone talking? There's kind of three ways to write to the register. I'll highlight each one of them and what they each kind of do. In this case, we're giving move B. Move B is probably the simplest one. It's just move byte. So like literally whatever byte we kind of given that blank is going to be written to DDRB. And in this case, configure port B as output. In the HCSA12, your study material should say this, or if you've ever been kind of given that, it should just say that output means 1. like logic one. And configure port B, we want to configure all of them as outputs because PB, right? We're handling everything for the seven segment display, so we're outputting to that. And we can just go ahead and write the whole thing as, actually, FF. So I'll just like set the entire register to that value. Okay. Yeah, that's probably the easiest one. So move B. The next one, here's the second kind of byte or the kind of, yeah, the byte setting or byte clearing values we have, which is B set. Move B is probably the simplest to understand, but B set is a kind of, it's not hard either. We can actually just look at it. So let's look at the B set instruction because you might have to do some kind of mental math here when you see these. So B set setting, oops. So on our left here, set bits in memory. So essentially that plus, if you look at the first page of these little this data sheet I have, the plus is OR. So you're just doing a logical OR essentially. So when we're, how do you know what hex value you have to put when you configure the port output? I'll talk about it again. But the B set, so move B, like I said, is the simplest. It literally just copies the byte, the whole thing into the register. In this case, we are setting the bits in memory by ORing them. So let's go back. I'm writing FF here just because configure port B as output. Our port B output is this here. We're going from 0 to 6. So 7 is not even wired, but I'm just going to write it as if 7 was wired, right? So each one is a bit in the entire DDRB kind of register, however you want to think about it. So, and I want to write them as all ones, right? And FF is in binary, it's just a byte as a byte would just be all ones. And so to configure port B as output, meaning logical ones, I'm writing FF to that DDRB. You could get away with writing like EF. I mean, if you want to be like exact, but there's no reason not to. It's not even wired here, so you might as well just write it as FF. Same thing. It ends up doing the same thing logically. So anyway, we want to kind of now let's see. So configure pin 7 of port P as output. So pin 7 is our last pin, PP right here. We want to configure that as output. And again, what do we say? Outputs are ones always, and inputs are always going to be zeros. And that holds true for like almost everything regarding these like questions. And we also established that B set is essentially just ORing DDRP with the value we give it. And we only care about that one pin 7, right? So if we have our byte, I'll just write it here, 1, 2, 3, 4. So this is logically what our byte is, right? We only care about pin 7, which is that first bit. So we want to set this to 1 only, right? How can we write this in hex? This is just ends up becoming 8 in hex. Oops. This ends up coming a 0. So when we OR this, it just ends up being 8, 0. Because we're ORing, we only want that pin 7 out as output, right? And pin 7 is our topmost bit in the DDRP. So we're just ORing it with 8, 0. I hope that makes sense. Yeah, there you go. Cool. So similar thing now, disable the 7-segment display by setting PP7 to 1. So it's pretty much the same thing. Yeah. So, and we can even use if you want to get like fancy, you can try and use like the third one, be clear or whatever. But do we need a hashtag for the 80? No, because it's not an address. It's just passing an immediate value. When you use the hashtag, it's to suggest an address. Isn't it the other way? How do you mean? Oh, is it the other way around? Oh, either way it compiles because you're right, it would work either way, but I guess we can put a hashtag here. I mean, like it's just asking for an immediate value, and like the address 80 or the number 80 would both work. Um, but essentially the next one, it ends up being the exact same thing. Why? Again, like it's kind of funny, like send this someone doing PTP, but disable the seven segment display by setting PP7 to 1. Again, we're setting PP7 to 1 here. So kind of like it just ends up, can we use binary for configuring the pins? Yeah, you could you could write this as like hashtag percent sign and then the binary, right? You could do that as well. I think it would work, but I'm just doing it as hex just to be a bit more compact. But yeah, you could technically write it as binary. So yeah, these are, they're not literally doing the exact same thing, but like for our use case, they are doing the exact same thing. So I just reuse the B set here, right? So branch clear, repeatedly read PP0 until it becomes 1. So we can go read the branch clear. I'm afraid it might confuse people more than it might help, but let's go check it. So if all selected bits, yeah, it might be a bit tough. It might be a few too many steps, but I might be better to explain it just like on the page. So the branch clear, let's look at this whole line as a whole, right? Let's see kind of like logically what this is doing. Repeatedly read PP0 until it becomes 1. So this is essentially an infinite loop, just like a while loop, like waiting for something to happen. So we're saying branch clear PTP, and we want to write a value to kind of list to like, how do I put it? We want to write a value such that we kind of only wait for one pin to change. And we want a PP0 pin, right? And if that thing is not changed, we branch to SW, which just puts us on the same line. So essentially what we want on this line is what number, and branch clear, we're looking for something to and, but I'll just say what number or what pin what pin as hex do we add here so that we read PP0? Remember that PP0 was the first one here, right? PP0 here. Remember when we did PP7? It's the last most, so we did this one. So this time when we're doing the first most, it ends up being, I won't rewrite it again, becomes 0, 1, right? Because that's the hex value for just the rightmost pin. And we only care about that one in this case. So hopefully that makes sense. It's the same concept. We're just, again, you could, if you wrote this as binary, it would just be like all zeros until the last one, which is 1, because we care about only PP0. And yeah, we read, yeah, the correct term for this is a mask. We're masking the bit pretty much. So if you're kind of comfortable thinking of it as a mask, that is the right way to think about it. I'm just trying to be more general about it. So yeah, hopefully that makes sense. Move B, simplest one. Again, we don't need to worry about any like and or semantics. We can just write exactly what we want. So I'll put the code of digit 8 via port B. So the code of digit 8, so we're literally writing to this PB here, our PTB register to get 8 printed here. So if you guys, I don't know if you got to the lab yet, you I think you did. Was it in 328 actually? Where you write to the 7 segment displays. And you guys remember like each bit of the byte responds like a kind of part of the 7 segment. Luckily, this time it asks us to do 8. So like it's the simplest one. You just write everything at once, right? But I'm just going to do an example if we had a different number, right? Let's say we had to do like 5, or let's do 3. So we want to get 3 onto this thing, right? And you see you kind of see the bit layouts of the thing right there, A to G. So if we wanted 3 here, like we kind of want to display it like this, right? That's what we want. Well, that's what we like, the kind of lights we want to light up. And so if we're writing this as a byte, A is our first one, right? So our A would be 1, B would be 1, C would be 1, DW1, E0, F0, there. And then I left one out because there is one more bit. We can just leave it. It doesn't matter in our case. If you remember from 3 to 8, that's the little like decimal sign that they have there. But as you can see, we only go from A to G, only 6 pins here, right? So it's not even wired for that last pin. We don't need to worry about it. But I'll just write it here just for continuity. But that would be how we would do 3, right? Same thing from 3 to 8, like whatever lab that was. In our case, though, today we're doing 8. So I'll end up filling this out. 8 is literally just all of them. And again, we don't care about this last bit. It could be 0 or 1. I'm just going to write it as a 1, like why not? Okay, I'll just make it 0 to make it easier actually. And then look what this ends up being. So again, we're converting from our binary to hex, right? Oh, I messed up, sorry. These are all ones. And I'll just actually, this is the best way to do this is just say X, so like I don't care pretty much. And so what is this end up being? This is F. 1, 2, 3. Like I'll take it as a 1 and just take this as an F as well. And so when we want to write, wouldn't it be the MSB that doesn't matter? Is it the MSB? I always forget. No, in this case, we're going from. Oh, you're right. It is. Yeah, because the way it's wired, it is the MSB in this case. F, and I put this as the don't care actually.
Let's start with the.
So yeah, and this is just a simple move B.
midterm.
So
Then
just write our FF to it.
let's
But again, that would be
do-
whatever number you want to kind of activate. Okay. So next one, enable the segment to display by clearing PP0 or PP7. Clearing PP7 to 0. So again, the kind of best way to think about this, I find, is that like a lot of the times it's just clearing here, right? Let's see. Does that mean that A is the least significant byte? No, A is the second most significant. It's like the second bit. So like, look at it like this. Imagine like an imaginary PB, like PB0, you can see, which is our like, is PB0 would be here. Like this is the 0th, 1, 2, 3, and so on. PB0, which is our G, is connected here. So that middle one, it's connected to this 0th. So I'll say and so on, right? And our last one, PB7, isn't even wired, so that's why I wrote it as don't care. But notice how here, when we had the set, it said setting PP7 to 1. I think that's like, it kind of gives it away in the words what instruction we have to use, and after that, it just becomes you kind of like picking the right bit. So this time we're clearing, right? So we want to use the be clear instruction. The difference between the three, I don't know if I got to be clear yet. Move B, I said, is just literally writing writing the register for whatever you set it. Be set, we're ORing the value, so kind of masking. Be clear, we're ANDing it. So we're clearing the bits we provide here, or like the byte we provide here, are the bits that are going to be cleared, meaning set to 0. So, and we only care about PP7 again, which is that our top bit. So we can copy what we did before and just write $80 here. Because we only care about our top bit. We only care about clearing our top bit here. And in this case, I wouldn't just kind of go willy-nilly and like say and write the rest, because we might lose actual information in the others, right? So we want to be kind of more precise with which one we clear instead of just writing FF or whatever. Then sounds good. Initialize the counter. So this part you have to kind of, again, I picked a kind of hard one. These older exam questions are a bit more difficult. They kind of trick you, but initialize the counter. This is the important part to look at here. You don't really see this anymore. So at that time, HE12 must display 8 on the 7-segment display for 300 milliseconds. That's the key number here. And why is that the key number? Because if you look at this line right after this, where this move B we're at, time delay of 100 milliseconds, right? And this is kind of just like a counter, like delay by looping. So let's kind of not say that yet, but we want to set up this loop first. So this is like a little delay, I guess, routine. Decrement the counter by 1. That's an easy one. Just the decrements, right? And branch to del if counter does not equal 0. This is our use case for BNE. Again, notice, remember before it would say decrement and branch, and then whatever the condition was, we would say DBNE. But if it's saying us, like, use these kind of comments is what I'm trying to say. It kind of gives you the correct hint a lot of the time. And then lastly, disable 7sec by setting. Remember setting, so right away it's a B set. PP7 to 1. And so, again, once we get our setting, we are just selecting our PP7 bit, which again, like every other time, was $80. And now we can go back here and fill in our move. So look, let's see what's happening, right? Time delay of 100 milliseconds. It's at del. So essentially, this is a little loop that each time the loop is or each time it's run, waits 100 milliseconds. And we said we want to wait 300 milliseconds total, right? So we could just write 3 here. Actually, I'll write it in hex just to be consistent. It's the same in decimal and hex, so at 3, right? So, and why 3? We're writing 3 to that counter because we want to delay 300 milliseconds. And that's why I wanted to fill out that loop first. So we understood what each iteration of the loop does and then how many times we want to run it, pretty much. And that's what these two are saying. So I can even mark these so we understand. Hopefully that makes sense. Is B clear and? Let's look at Be Clear exactly so I can show you guys exactly what it is. It's a bit complicated, and that's why I didn't want to go all the way down, and that's why I just focus on like just worrying, like mainly worrying about like how to select the bit first. Let's actually go see what Be Clear is, right? Oh, what is going on? Be Clear is here. So we're ending it with the inverse of what we provided. So if you kind of understand what that is doing, like if we select like whatever, like think about what that's doing if we're ending it with the inverse of what we provide. So if we provide it with 80, so we're kind of selecting that first bit, inverse that. So that first bit is 0 and the rest are 1, meaning whatever. And if we're ending a value with that kind of thing we just set up, all the other bits are going to remain as they are. And that one that we kind of selected is being set to 0 because it's being ended with 0, right? And that's the kind of way to think about that. So yeah, again, that's why I mean you can clear up any questions if you look at the instruction set. It tells you exactly what's happening here, right? But if you kind of want to be lazy, and I wouldn't recommend it, but because it worked out in this question, but I don't know how it's going to be in your actual question, you can just kind of look for that clearing and setting, right? And then the only thing you have to worry about is understanding where to kind of how to select the right pin that you're looking for. And that's this question done. I mean, it's not like you can see as if you kind of work through it, it's not the worst thing in the world. The hardest part is kind of conversions between binary and hex and just selecting the right instruction. And I guess you might get tripped up on like we got let off easy with that 8, but if you get like a weirder one and kind of mess it up, you could lose marks there. But that's why at the beginning I mentioned take note of these like PP pins or whatever they're called in yours. PP, like the input and output pins essentially. Notice how these only go 0 to 6 and it's wired like G being 0. and they're always big endian, meaning like a most significant bit first. That's the best I can best advice I can give you. Just look at those pins. That's where like most people lose marks on these, because this whole midterm exam, to be honest, it's not too complicated. But if you can kind of see how you might be like off by one on a loop, or you select the wrong address, or like when you're trying to make the conversion between binary and hex, you format it incorrectly, so you might get marks off here, and it just kind of snowballs. So that's why it's kind of important to make sure you're not just copying off memory of what you saw, but understanding as well like the exact parameters of the problem, because they don't really mention it here in writing. At least you just kind of have to see it and understand that. Okay. Can we do #3 instead of $3? Yeah, I originally had it as without the $, but it's like I would, anytime you're kind of involved with writing or masking or whatever, working with a register, I would always do it in hex just to kind of keep it mentally like just kind of mentally consistent, I should say. In this case, you could leave it as just 3, yeah, and then it like logically would make sense. It's just a #3. But yes, okay. We'll go to the next one. So another just general programming question. Kind of the same as the last thing, a combination of the last few. We're just given comments and we just have to kind of fill out the table so that it's kind of follows the comments. That's it. So let's look at it. There's no funny instruction count or anything, just filling it out. So let's see. Start the following code at $4,000. Cool, easy. Okay. Make accumulator D have value 8127. So what instruction can we use to give accumulator D a value? We don't necessarily need to use our like little memory sets or anything like that. We can just use LDD, right? The simple kind of bread and butter instructions. So we'll just use LDD. $8127, right? Next, arithmetic shift left contents of accumulator A. So we're just doing a left shift of the thing. Let's go look in these because I don't even know what the instruction is for this. I'm gonna assume the name and just kind of look based off that. So arithmetic shift, I assume it's gonna start with AS. Yeah, so this is what it is. So we wanna, I can scroll up, actually fine. It was just a arithmetic shift left of accumulator A. And if you spotted it, it's right here, which is this instruction here. And there's no like input to this. You just run the instruction itself. Cool. I should say you don't need to fill out every single one, right? It's dependent on the comments of what you're given, right? Anyway, logic and of accumulator A with value 5A. So let's look at the thing. I know this instruction is and A, but let's see exactly the format of how we're supposed to specify our immediate value. So and A. So logical and A with memory. What's this saying? So our A register is whatever's stored in the actual A. M is the value we're passing in essentially, and it's this kind of thing here or this here. Notice how it works with so many different things, right? And in this case, look, you can use the hashtag if you want to. You don't have to though. You can use it without the hashtag. But if you don't use the hashtag, you kind of have to work it out on your own. But either way, we'll just keep it simple. So logical and, we know it's and A. Logical and, so the instruction is and A, and our immediate value that we pass to it, in this case, I'll use the hashtag. One is logical, one is arithmetic. Yeah, what is the difference with ASLA? I can come back and we can look at it together, but yeah, that's the answer. And then this is with $5A. So let's see the difference. You said you asked a question, what's the difference between ASLA and LSLA? Let's see. So ASLA, arithmetic shift left accumulator A. Let's see. Logical shift accumulator A to the left. So let's see, you can literally see what it's doing, I guess. Logical shift left. So it's shifting every bit into the right, into the left, and I assume, yeah, okay, so this is what's happening. Logical shift left, whatever was in like that kind of top bit, it just gets kicked out into C. And then the new bit on the right becomes 0. And if I would guess, on A, it just kind of wraps or something. Or not. It's the same thing, I guess. Yeah, it changes. That's what I would have thought too, but I guess not. It looks like the exact same thing. Arithmetic shift left accumulator A. Let's see. Maybe I missed the difference. Oh yeah, it is only a right shift thing. Yeah, because the B on the arithmetic rights gets like put back into itself, and I would assume on the other way, LSLD or something, or sorry, whatever LS, um, the right way. Yeah, so that's what it is. It just doesn't do anything on our like left shift, but on the right shift it does matter. Cool. So yeah, fun fact, I guess. Just as like a kind of anecdote, a lot of these microcontroller or like these older instructions, even new ones do this as well, to be honest. And you'll learn this in 608 if you for people take in computer eng. But a lot of times the designers of these instruction sets or just the architectures in general will kind of just to maintain that kind of like continuity or like familiarness, they'll even if like logically they do the same thing, they'll include both instructions because they don't really make a difference. Um, yeah, just like a tidbit, doesn't really matter. Would it technically run put LSL in this case? If you're running it on the actual microcontroller, I think you're right. It wouldn't make a difference. But if they're asking you for yeah, logic and accumulator A with, oh, sorry, they're asking you for the arithmetic shift, I would put ASLA. Um, I guess you're right that like if you actually were to run this program on the HCS 12, it would make no difference. But if they're asking for arithmetic, I would put that one there just in case. Yeah. And then a simple one, increment contents of accumulator A. We know that's just inc A. Again, you can, if you're following along with the instruction set, you can see what it does, but it's pretty simple. And then go to start just unconditionally, right? No decrement this or branch if this is equal. So our unconditional branch is just branch. And we put our label start. And that's that question. Again, but like since it's like I put this one down just because to be honest, now that we're kind of more used to looking at the instructions and looking for them, this question's pretty easy, I think. It just again following their comments, following their instructions, cross-referencing the instruction set, and it should be pretty easy. Yeah, I don't think there's too much difficulty on this one, so I'll just go next. ATD converter must be initialized with the following settings. So essentially what this one is, the registers, the ACS12 has some registers. This is one of them, the ATD converter, the analog to digital converter. What this question is essentially going to ask you to do is set up that register with some like certain parameters. And the parameters are given to us right here, right? And so all we're really doing on this question is reading the parameters, building like our kind of register that we're going to filling out a register essentially, and then putting that value here once we're done. Let's do it step by step. Let's see what our first bit is in this ATD CTL5, right? Left to right justified data. So we see we're right justified. So I'm going to put this as a 1. D sign, unsigned or sign, unsigned. So we're going to put 0. Scan single or continuous conversion sequences. Perform a sequence. So I'll just keep it on top. Sequence of measurements. So it's not a single one, right? One sample one or several channels. We only want channel 2 here, so we're only going to say one channel. Put a 0 there. And then, so this one here is always zero, no change. I guess we'll just put zero just for ourselves here. Actually, I'll leave it just so to put emphasis that's always going to be zero. And then channel select code is just binary selection. We want channel two, so AN2. Um, it's just going to be 0, 1, 0. Why? Because we're just following AN2. So cool. We built our little what we're gonna like kind of mask the register with, and now we just want to convert it. You see our little hashtag there, our hashtag $. Same we've been doing this whole time. Convert this to a hex value and uh, pretty much just write that to the thing. I'm too lazy to remember what this was. If anybody beat me to the conversion, you can put it in the chat. A2. It's A2. Yeah, so fair enough. A2. Shouldn't scan be 0 because I want the sequence to stop and stop. They're both going to stop, right? But it's just a single or continuous conversion sequences. And we want a sequence of measurements being plural, so I would assume a few conversion sequences. Stopping is handled like outside of this register, so like it's just their wording is a bit funny, but just kind of like this one is a kind of funny question because you get these in the final as well, but just kind of more registers to configure. It's just kind of following their wording and hoping that they were clear enough with their wording. It's a sequence of measurements, right? So I logically wouldn't think this is a single conversion. But if you believe otherwise, you could switch the register, update the value that we're flashing or we're using move v with, and write your own whichever one you want, right? It's a single sequence with see, it's a single sequence with multiple measurements in the sequence. A sequence. Okay, I could see that as well. I could see that as well. Sequence of measurements. Yeah, yeah, I could see that as well. Fair enough. We can switch it to 0. And this will just become 8. Perform sequences. Yeah, this is why I say this question's a bit tricky because like it's in the wording, right? It's not as like kind of dry as the past few questions that we've been doing, which is like it's either right or it's wrong. This one is kind of up to interpretation on a lot of them. I think it happened on our either midterm or final where like the wording was like not as clear as you would hope, and some people kind of argued like they wrote what they assumed and then got it wrong, but then they argued it afterwards and they got the mark back. But like I would say you're actually right here that it is sequence, and leave it as 8-2, but. Yeah, you're kind of relying on the wording here. Other than that, though, that's pretty much it. Yeah, that's pretty much it. Solved all the questions here. Realistically, you're gonna get. I would not be surprised if you get every single one of these questions, like variations of them, obviously. Not with the exact same like program layout or anything, but like it's gonna be like a stack question, a kind of e-clock question. You're for sure gonna get one of these like little like 7-segment questions. Yeah, again, if you have any past midterms, how many questions will be in the midterm? The one I'm looking at right now from 2011 has 5. Let's see, 2012 has 6. But like question 1 is usually multiple choice, right? So those 5 and 2 hours, dude, like they gave you, I don't know, 2, 3 hours, or they gave you, like, I'll be honest, most people when I wrote it were done in half an hour. Like you're in and out. Let me hover over this question for you though. Yeah, it's not, I'll be honest, it's not too hard of an exam. Again, it's the little things that could kind of trip you up. Like it's going to be these questions that I kind of went through here. Maybe one or two, one extra maybe one taken away from here. They might like switch one out, and then multiple choice. But the multiple choice is not too bad. It's like, let's see if I can get some multiple choice screenshots and just add it to a page here or something for just to fill out the end. I'll insert page after. So I'm too lazy to like get rid of the actual answers, so we'll just kind of talk about it together. The short answer questions, like the short answer question will be like that e-clock question, for example. That is a short answer question. Yeah, it's like there's not most of the questions have 6 questions total, with the first being MC. Yeah. Yeah. So if you like, I don't know, do they give you any past midterms on the, even if they're old midterms, they're still like, this is one of those classes where even the old midterms are good. These are the examples of multiple choice. Not too hard, to be honest. Which instruction is used to exit a subroutine? None of these, like RTI, does the RTI even exist? Let's see. I know obviously RTS is the answer, but like RTB doesn't exist. RTF doesn't exist. RTI, that may be, I think that's a MIPS thing. I'm just remembering from a different instruction set, but RTI exists, but this is obviously something else. Return from interrupt, right? So that's why it would be RTS there. I'll leave these ones. So I'll just like, I guess I'll solve these on paper as well. So it doesn't exist, doesn't exist. Return from, and then str doesn't exist. Or at least it's obviously not a return. Next one, how many memory locations can the HCS812 access without extended memory? Okay, this like, obviously it's either one of these two. So I'll just say it's not this one. It has to be like a power of 2. That's the first thing you have to think about right away, right? So it can't be 64,000 exactly. It can't be 32. So let's go with these 3. I'm like, I'm cheating because I kind of understand like the architecture, but it's a 16-bit architecture, right? 16 bits, meaning the max like address space you can have is 16 bits. So it's just let's see, 2 to the 16 equals, oops, 6, 5, 5, 36, right? It's that number exactly. I can run a little like Python, not check, think to check. Oh wait, can you not do this? You have to do like import math dot pal. I just want to make sure it's the exact number, right? 2, yeah, 65536, cool. So why would it be this one and not 65535? Because that's like off by 1. You might make that mistake. Simple, right? It's not asking us the highest index, because if we have 65536 like possible addresses, right? It's just asking how many locations are there, not like what's the top index. If we were indexing it and just say like what's the highest index, what's the highest like actual slot in memory, it would be the one ending in 5. And why is that? Because when we index memory, we start at 0, right? But when we're just counting locations, we don't count at 0. We count like literally how many locations there are. So starting at 1. So I can write that as well. And then, yeah, that's pretty much it. And then how many address lines are required to access 32 memory locations? I mean, by the logic we just solved, so we said 16 bits is 655536 divided by 2 for 32K. I'll just close that out as well. Divided by 2 for 32 is 15, right? Like 32 is what, like, it's like what? Because it's like 16, wait, 16, 384, and then what's times 2? It's like 30. Whatever, 32K. But like that's just to say that it is 2 to the 15. Yeah, 32768. So that's the exact number, but 32K. In what mode will the other answers be correct for for B. What do you mean? In what mode would the other answers be correct if they ask on the midterm? Like the only, I mean, like I don't, like I can't answer for the last three because those are just like arbitrary numbers. But if the thing was saying like, what's the highest? Yeah, 2 to the 5 is 32, and yeah, I mean, other than the expanded. So for B, well, 64, yeah, 64, 30,000, 32,000 are useless, 32K is whatever. So yeah, like I said before, the and one ending in 5, if they were to ask, what's the highest actual memory address, it would be this one. Because if we have, 65536 memory addresses and we're indexing by 0, so that the location, the address of the highest address would be the one ending in a 5, right? Just n minus 1. How do you know to use 216? The HCS12 is a 16-bit processor. Like, um, yeah, I don't know. Like that's just you should learn that early on. If it's a 16-bit processor, like there's 2 to the 16 possible, like the highest math it can do. I mean, like let's assume the highest math it can do is with 16 bits, meaning 16 bits of address space. Like if it was a 32-bit processor, you have 32 bits of address space, 64 bits, so on, right? Yeah, like I kind of jumped to it, 2 to the 16. I know 2 to the 16 is that number. I know 2 to the 15 is 32K, but you can kind of work around it with like logarithms if you want. But yeah, like but you get used to, like, especially when you kind of study for these classes, you get used to the powers of 2 and you just kind of like recognize them on the spot. Yeah, if anybody has any questions for any other ones as well, feel free to ask. But other than that, that's pretty much the whole thing. The only thing left that I would recommend like looking at, I don't know if I have a question of it. Thank you, good teacher. Can you 7 segment pins again? Yeah, sure, we can go 7 segment pins. The last thing I would recommend, you know what? I'll just add it. No, it's not really good because it doesn't show how to do it. Yeah, never mind. If you can find it, like there has to be questions about like the A to D, like ADC, like the analog to digital conversion, or just the math of the question, like what's the resolution, what's the difference, like that type of thing. I don't have a problem with that, just because I can't even find one on the midterms. I went to this one, so. But I would really recommend getting comfortable with that as well. Yeah, like the exactly, that's the one, like the interpolation one. Like they for sure do it in a class. Like it's one of the later classes before the midterm, but it's like be comfortable with like the resolution of this ADC, or like if this is my final result, like what bits, like that type of thing. Just like the kind of ADC like math. It's easy questions, like 1 mark, 2 mark questions, like short answers. But if I had to bet, they're going to be on it as well. It's on the sample midterm. Exactly. On the sample midterm, perfect. You got it. But can you go to 7 segment pins again? So I'll go to 7 segment pins again one more time. So what are we looking for, right? So this is the same diagram they pretty much use. I'm just gonna like assume this is the diagram you guys see as well. PB0 to PB6 are your output. Why are they output? Because they're literally connected to the 7 segment display, right? So I'll just say output. So every time they talk about output pins, we're talking about the PBs, right? And it says it up here, but so designed to monitor when switch is on, the PP0 receives with logic 1. Okay, it doesn't really mention much, but these, oh, let me not do that. Input here. So right away, when we're talking about input output, that's what it is. I mean, you can see why this is input, right? We have our like VCC and a switch depending on, and this is kind of mirrored for each one. And so it's essentially saying once the switch is thrown, all these switches will get VCC, and it's up to the microcontroller to decide like what we do with those values, right? So let's talk about these pins again one more time. So it's just the only thing to kind of think about here. We have PB0 to PB6. So like what that would look like in binary is, or oh, well, I guess how would I do this? I'm not trying to write out like PB0, PB1, PB2. I'll just say values. Uh, And then this would be technically PB7, but it's not, right? So we're just going to go like this. And all you're kind of looking at when you're doing these questions is like the hardest part is converting from binary to hex. If it's going to ask you like, oops, configure, like for example, down here saying configure pin 7 of port P as output. So I'm just going to say like that. Let's say like I want to find pin 7 on this, right? Pin 7 is literally just this one. Or I guess it would be this one. It's a bad example. Let me go to the follow the question. Um, let's see. Okay, maybe this all it was a bad example, and I'll just switch these to P. So it's logical when you if you look back at this. PP6, PP7. Um, configure pin 7 of the port P as output. So forgetting like the rest of it, and we're only looking at that pin 7. What are we doing? Like this is our PP0 is our rightmost, PP7 is our final one. And if we're doing PP, this is actually PP7 as well. So I'll just write that. So if we're looking at our seventh bit is like 7th bit would be our leftmost or like our on the end because we have 8 bits total, right? It's the same thing as like how many addresses there are versus the actual indices of the addresses. We care about this bit. This is PP7, right? This pin. So when we're setting it to 1, that means literally if we want to set this to 1, look at our new binary number. It's just as simple as converting this now to hex. And so that's what kind of it's not too bad once you kind of wrap your head around it. Just using it to select, and then this is like how it's done even today, right? It's not like an old concept. Um, it's masking, if you it's like bit masking pretty much. That's the actual term for it. But the style of this question will be very similar. The only difference is like it's going to be like what instructions, like it's just the kind of layout of the code they have there for you. That's it. But the actual like select is the same kind of select, right? Is if they're asking you for like the pin 7 of port P, it establishes the input because it's on the right here. So pin 7, you literally like you can see it says the pin 7 is the high most. But yeah, make sure for this question to look out for the numbering of these. They won't like throw random numbers in there, but you see how this one ends at like it's 0 to 6. Oops. It's 0 to 6 and this one's 0 to 7, right? And in our case, 0 to 6, it doesn't matter, but sometimes they'll start it at like PP1 and it kind of like messes you up a little bit. So take note of the start and end position of these pins because like it'll change what values you're masking. But yeah, that's pretty much it. If you have a simple midterm and it has like, it's going to have these similar questions, go through their questions. You can try like not looking at my answers and looking at these questions as well. And yeah, don't be too worried about his exam. It's not going to be bad, to be honest. So yeah, other than that, if you guys have no more questions, you're free to go. We're done. Yeah, have a good night. Good luck on co-op applications.